Good evening, students. Welcome back for another very important lecture on inner transition elements. Inner transition elements. Students, it's a very important topic and we will be getting questions from this topic in the exams. So, students, what I am talking today is a very interesting and something very important. We are now coming to the last part of the transition elements which we started, students. And as you will see, what we are talking is inner. What I am talking is inner transition elements. What do we mean by inner transition elements, students? First thing we should know, what do you mean by inner transition elements? When I discussed the transition series, students, I discussed 3D series, I discussed 4D series, 5D series. This is another series, student. And here, when I discussed the 5D series, students, at that time, what we said, this was starting from scandium, and what we have shown you, and this was from terbium. And what happened in the series here, if I go back, then we will be able to see what we were talking about, students. Little bit of the periodic table. If we have the periodic table with us, which we told you, shown with you. These are the first transition series which we have shown you, students. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, then ytterbium, 3D series, 4D series, 5D series, students. And what we found, this was the story here. First transition series was starting from scandium 21 to 30, ytterbium. But as soon as we enter the 3D, 4D, 5D series, what happens? As you can see, you have lanthanum, which is 57. After that, you are getting hafnium. And in this case, you are getting actinium, 3D series, 4D, 5D, and 6D series. You are getting actinium 89, and after that, immediately 14 elements are missing. I am talking of hafnium. I hope you can
Okay.
understand what I try to say and why did I do that.
Yes, sir.
Now, the 14 elements are missing from group 3. From which group? Group 3.
Group 3.
Group 3, what we are saying that group 3, this is our group 3, student, group number 3. Group number 3, here you have lanthanum, 21 and 30, add 18, 39, and then you will add 18, how much you are getting? 57 lanthanum. So here, what is happening, students? After lanthanum, what happened? How many elements are missing?
14.
14 elements are missing. And then the next element here was hafnium. So 14 elements are where? So what was the atomic number here? 72? 72. So the 14 in from the group 3, you are saying group 3, which is your transition metal series, the transition metal series, students. What is the period number? Tell me, what is the period number here? Group 3.
Uh, it is period 6.
5D, na 6s2, sixth period. Period number
Yes.
6. So from group 3, after lanthanum, the atomic number of which is 57. And if I see the electronic configuration of the students, so what you are seeing in the outermost, you have 5D1 and 6S2. This is our lanthanum 57. What is the name of this? Lanthanum.
Lanthanum.
And after that, when you come to 58 student, that 58 is our cerium. 58 is the cerium. Cerium is very important element, 58. And as you can see now in the cerium, what has happened, students? This is the first electron starts entering into the 4f. 4f1, 5d1, 6s1. This is how the configuration has been written. Now, about the electronic configuration, there could be somewhere some little bit of discrepancy. They may show 6s2, 4f2 in some books. This is experimental observation, not our observation. For your information, students, electronic configuration are determined experimentally. Got my point?
Okay.
Sometimes, in some cases, you can see small exceptions or small changes because the energy levels gap is very small, so electrons can be either side.
Okay.
So they determine experimentally, spectroscopically, and then they list it to us. And sometimes we know the sequence how to make them. Somewhere we do not know because experimentally they find that configuration which they have listed. We have to then memorize it. If it is important for the exam, we have to memorize that case,
Okay.
which will be exception or different. Got my point? Because this is experimental. The rule is not
Okay.
applicable, which we are using. All right. Try to be with me. Pay attention to each and every word. Student, every word I write has a meaning, has importance for the exam. My first question is, what are inner transition elements? I have not gone beyond that yet. When I write a word, I have to explain it, student. So inner transition elements are those which are actually coming out from the transition series and which are coming the first inner transition element which I'm talking of are those which are coming from group 3 and period number 6, and that series is what we are calling as lanthanoids, students.
Lanthanoid series.
And in lanthanoid series the 4f orbitals are in the process of being filled, or s f orbitals are in the process of being filled. So how many will be their students? As you can say 4f1, 2, they will go up to
14.
f14. So those 14 elements which were derived, which are actually belonging to group 3 of the sixth period or 5D series of the transition elements have been now named as lanthanoids. So that is why we are saying they are inner transition elements. They are actually part of the transition element, inner transition element. They are born out of the transition series.
In, okay.
So this is the first one which we have said inner transition element. First series of which is I'm talking of the there are the F block series consists of two love series. First series which I have talked is which one? Lanthanoids. This is
Lanthanoids.
what is 4F.
Sir, these elements have to be memorized, lanthanoids and
No, no, no,
actinoids.
nothing. I will explain to you everything. You wait and watch. What has to be remembered, what not, we will tell you. It's not possible to
Okay.
remember the names of all the elements. Only a few ones, lanthanum, cerium, the first, the second, and the last should be known at least. Should be known at least where it
Okay.
starts, where it ends. And the atomic number series, we have already explained how easy it is by using the magic number
Yes, sir.
concepts.
Yes,
So
sir.
4F is born out of the sixth period. After that, I have shown you that when I will come to actinium, when I will come to actinium, actinium is 89 students, atomic number 89. Okay? Add add 57 plus 32, you will get actinium because 4f orbitals are also there now. And after actinium, again, you will see that you come to the next element, which is thorium. And from here, you will see that the process of 5F1, 6D1 or 2, and 7S2. So the 5F orbital starts being filled from thorium. Thorium. So this series we will show you, and this series is what is named as actinoids. They are lanthanoids, and these are called student actinoids. What are they called? These 14 elements are called
Actinoids.
actinoids. Actinoids. So 14 elements which are following. ठीक है? The
Okay.
important point to note is that, what is the important point to note? First thing, these are the inner transition elements because they are born out of the, what is the group number of this second
Group 3.
group 3? The second lanthanide series, in the lanthanide and in the F block element, I'm saying there are two series. The first one is the 4F, second is the 5F series. 5F series, and this is our 4F series. 4F series. ठीक है? This will belong to
Okay.
7th period and group number
3.
3. This question has been asked in paper. All right. So first question to us is clear that these elements are the part of the group 3 of the transition series. So instead of putting them in group 3, because our table will become very, very long and lengthy, we have decided to put outside them, because here the F electrons, F orbitals are being filled, are in the process of being filled. So inner transition elements, basically we are saying, are which one? You have two series. Two series. First thing, question number 1. Question number 2, what are F block elements? What are F block elements? What is your answer, student? 30 seconds.
The F block elements are the inner transition elements, which consist of two series lanthanoid and actinoids, having 14 elements in each.
And that means the electrons, the outer electrons are entering into the
Into the F orbital.
F orbital. When electrons enter into the S orbital, outermost S block, when they enter into the P, outermost electron into the P electron, you call P block element. When the outer electrons entering into D subshell, you call D block. And the outer electrons are entering into the F subshell, or F subshell is being in the process of being filled, students. These are, that will be called F block elements. ठीक है?
Okay.
And there are two series. One is 4F series, other is 5F. One is called the
5F series.
lanthanides, other is called the actinoids.
Actinoids.
Now the question to you is in the form of assertions in the paper nowadays. Are lanthanum and actinium F block elements? Yes or no? You have to think. Before you answer any question, thinking it will be required. Once you are with me, students, think, activate yourself, energy requirement, and mentally alert, pay attention. My question is that, what is the question? Is lanthanum and actinium, student, F block elements? Yes or no?
No.
Okay, give me the reason.
They are not F block elements because the last electron does not enter in the F block.
Okay, that's the correct answer. Sometimes you see the questions are asked where we can do easy mistakes. They are in the series, they are put in the same series. ठीक है?
Yes, sir.
Second question, why they have been kept in the series of, why, if you are saying lanthanum is not F block element, why it is kept in the series of lanthanide, students? Give me the answer, 30 seconds. Small
Its
questions have been asked.
its properties resembles those of F block elements.
See, the answer is right. Why you say F block? If I am talking of lanthanum, you have to talk of lanthanide series, because the property of the lanthanide resembles that of the lanthanoids. And so much so that the name has also been put according to this as lanthanide or lanthanum series. This is also called lanthanide or lanthanum series. Students, got it?
Yes, sir.
Okay. How the questions are framed. There are no big questions for any exam, let me tell you. Questions are small but require attention and thinking. Students, slight mistake is out, we are out. Everywhere it is not, the questions are not difficult or not big. Those who have not done thorough study, they are in trouble. Okay. So you have said what are transition element. You have also defined what are F block elements. When I write a word, I should be able to know the answer. What are F block elements? So you said those in which the electrons are being filled in the F
F block.
subshell
F subshell.
or F orbital. They are the F block elements. Then we ask the question number three: is lanthanide or actinium? These are F block elements. No, they are not F block elements, but they have been kept in which series? They have been kept in lanthanum has been
Lan-
given lanthanide series because properties
Resemble.
are very similar.
Okay.
So much so that the name has also been put according to this lanthanum series. Lanthanide series is derived from lanthanum. So is the case with actinium. Student, actinium is 89 and lanthanum is 57. So here also their actinium resembles actinide series in their properties, and that is why even the name has been given as actinide series.
Okay.
Therefore, students, we are now today discussing about the inner transition elements, the F block elements, in which we are talking of two series. The first series which we'll be discussing today will be the lanthanoids. Lanthanoids, student, and sometimes in they are referred to as LA. When I say LA means
Okay.
not lanthanum, it means a complete series may be represented like LA. When you will say La3 plus ions, that means lanthanide series. We are talking of lanthanide series, which we have before us. So, students, here basically it starts from 58, which is cerium. 58 is my cerium, and it is going up to which element, students? 71. What is that? Lutetium. Lutetium. So
Lutetium.
we are expecting if this is 4F1 series, it will go up to 4F14. But what will be happen to the
4F14.
electronic configuration? We are going to have a look on that also. We will be looking
Okay.
the electronic configuration. That is why the table has been produced from the book in order to see the electronic configuration. It is not possible to remember the electronic configuration of all the elements, but few important ones have been asked in the paper, students. So that where we have to know for certain reasons, because certain elements, so oxidation states become very, very stable. Those questions will be there in the paper, students. Let us see what I am talking about. Now, here I am going to talk about electronic configuration of the lanthanides, students. Now, what are the inert gas element? Helium, neon, argon,
Argon, krypton,
krypton,
xenon.
xenon. What is the atomic number of xenon? 2, 10,
10,
18,
18,
36,
36,
and 54.
54.
So, if I say if I say student LA is 57, so you are saying okay, what you are saying, student, this 54 XE inert gas,
Okay.
and this is belonging to the sixth period. I am immediately saying 6s2. Okay.
Okay.
Now, what is further? How many? 54 plus 2, 50. 6.
56.
And
Wait,
there
wait,
is
wait.
the next one is 5D. You are saying 5D. And 4F, after this is 4F0. Does it complete the 57?
Yes, sir.
Okay. I am learning the electronic configuration of these elements. 54. There is no electron in F, therefore it is not belonging to F block,
F
but still
block.
it is belonging to lanthanide series. Okay? They are
Okay.
kept in that lanthanide series. So what happens after that, student? I am coming to 58. 58 is what is the name of the element? Cerium.
Cerium.
So if you are saying 54 Xe, then you have
And 6
6s2
2.
and 5p1
56.
and 4f1. So here you are seeing that first electron is entering into the f orbital. In certain places, you may see that in this NCRT book, what he writes, cerium 4f1, 5d1. Okay, NCRT book. 4f1, so first electron is put in here. Okay, this is NCRT. In one book, he says 5d2, 5d2. Still, he is not putting. But okay, this is the first element, which is our cerium, in which we have got one electron in the 4f. ठीक है? We can
Yes.
now go from cerium. The next element is 59, student. 59. What is the name? Praseodymium.
Presidium.
PPR. Interesting thing. Now this atomic number is 52. This is 54. Okay? And here
54.
now you see that there is
6
nothing in the D. There is nothing in the D, student. 4F. How many he is writing? 3.
3.
And 5D0. 5D0 and 6S2. See what has happened? Once the start filling of 4F takes place, the D electron also is moved to the 4F. Now 54, how much is this? 54 and 53, 57 and 59.
59.
4F3, Prasidonium. And after that, students, which one is the next one? Neodymium ND. Neodymium ND is how much? 60.
60.
I we need not write this. So what is the happening in this 4F4 and then 5D0 and
6s2.
6S2. You can see that this is the outer shell. This is called penultimate shell. We told you
Yes, sir.
this is the outer most penultimate, and this is called anti penultimate. Anti penultimate. So the electrons are being filled in a F which is deeply buried. F4F is deeply buried. Is embedded inside the atom. 4F is embedded inside the atom. One word I'm using, which I will explain when I will talk of the properties of lanthanides. It is buried.
Okay.
It is buried. It is embedded in the atom, student, because you have outer ones here. Okay. Now there is a poor screening of this, and the nucleus will have effective nuclear charge which will attract, I mean, pull these electrons towards itself, and it will pull 4F more towards itself. They will be pulled more. There is a consequence of everything, and when we try to explain the experimental properties like spectra and other things, you'll see that. So you have got ND, but and where is ND? Neodymium. And here promethium 4F5, 6S2, okay, no problem. Samarium 4F6, 6S2,
6s2.
And once you come to European student, European, you are seeing 4F76S2. European, important element, so we have written because the plus 2 state will become important here. European, where is European is 63, EU is 63. This is 4F7 and 6S2. 5D06S2 student. This is half filled. See the half filled and completely filled configuration. So that this provides more stability that we already know.
Yes, sir.
And after this comes gadolinium, GD. This is important now. What is the atomic number? 64.
64.
This configuration was asked in the paper. Now there is a reason for that. The next electron is seen in the gadolinium in 5D16S2. See 4F7, 4F7, 5D1, 6S2. Because this is half filled, half filled. So one electron is gone to the D.
Okay.
One electron is gone to the D students. Let me see. Gadolinium, seen that? Why did we? Okay, we'll show you what is the reason. Something is important here. Questions can be asked there. Where is a
Okay.
red pen? Gadolinium student. This configuration is important. Gadolinium. This has got 5D. There is electron in 5D. There is an electron in 5D in this one. Cerium 5D here. Where is another 5D in the last one? So there are how many about in the series? 1, 2, 3, 4. There is no electron in the D in other cases. This is a point to be noted. We'll talk about that. All right, this is gadolinium. You have got one electron in the D, and after that you see that it goes to the next. Then it becomes 4F9, 6S2, 4F11, 12, 13. No problem. But once we come here, what has happened? 4F13. This is 4F14. This is completely filled ytterbium. What is happening to ytterbium student? YV70 atomic number. Terbium is 4F14. 5D0 6S2 6S2. ठीक है?
Yes, sir.
And what happens in the last, which is lutetium? Again, another electron is going into the D because it has become completely filled. 71. 4F14, 5D1 and 6S2. So this is a electronic configuration basically, and the elements which has got electron in D orbital, 5D orbital. How many elements? Which are those? Lanthanum. What is the next one?
Cerium,
Cerium. And
then gadolinium.
gadolinium is important for writing the electronic configuration in the paper because you can see that 64. And last one, lutetium.
Lutetium.
The important point, they have 5D1. 5D1. This is how we learn the thing, students. 5D1. Rest 6S2 and then 4F. So as in on is already there. 54. So we only balance this. And this is not the outer shell, as you can see. Outer is the S1, then D, and then N minus 2. So in general, you are saying N minus 2F, N minus 1D, and NS. NS2, they are showing, and then can be 0 or 1. And 1 to 14. This is the general electronic configuration,
Yes, sir.
friends, for the lanthanide inner transition elements. Inner transition element, this is the general electronic configuration.
Sir, it can be N minus 2F0 to 14 also.
Well, if we have, if f is 0, then it is not belonging to f block, that we have already defined it.
Okay.
That we have already defined. There should be at least one electron in the f to be called f block.
Okay.
So general electronic, only lanthanum and actinide, they have been put because of the similarities in the property. So we are saying they are not f block elements. We already defined general electronic configuration. Okay. So how many are having electron in the D? Which one? Gadolinium, cerium. These
Here,
names
land.
are becoming common to us. Cerium, gadolinium, lutetium, lanthanum. At least four we have been able to remember.
Okay.
Rest looks to be quite different, but with one more at terbium, because it is coming before this. YB, YB. When we will discuss the oxidation states, we will again see which is important and how. Okay, students, electronic configuration, question is, we have answered this question very well. The electronic configuration question can be given. Student, write the electronic configuration. One question has been asked somewhere in the exam, student. Gadolinium, or they can ask for cerium 58. What is the atomic number of gadolinium? We just told you. Gadolinium atomic number
Gadolinium is 64.
64. And they can ask for lutetium. We already know lutetium. We have already shown you. This is lutetium. So at least few electronic configurations should be known to us, which are becoming important for us for the exam. It has been asked, so
Okay.
we have to know it. As I said, sometimes it is not possible to derive rules for everything, and then we have to learn them and memorize also, depending on the experimental information provided in the book. We are relying on the NCRT book, so we are using that table. Second important thing, student, let us see about the atomic and ionic sizes. What is happening, students, in this case? What is happening in this, students? There is something very important which is of interest and will be asked in the paper, student. That is always asked. What we see, you are going from lanthanum to cerium, praseodymium, and so started with 58, 57, and the last one 71, 70. ठीक है?
Lutetium. Yes, sir.
This is our 4F series or lanthanoids. Lanthanoids. As we go from lanthanum to lutetium, students, what we find, there is a overall decrease. There is an overall decrease in atomic and ionic radii. There is a decrease, and the most stable oxidation state is 3 plus. Therefore, as I said, 3 plus. So they have been shown as La3 plus. Plus 3 is the most stable state. So ionic radii, when I am talking of La3 plus ions. What do we find, student? There is an overall decrease in the atomic radius. and ionic radii with increase in atomic number. With increase in
Atomic
atomic
number.
number. And from lanthanum to lutetium. This is also known as lanthanide contraction. We have already learned one more lanthanide contraction, which we already know. We will explain to you that also is a consequence of this 4F this. So this is important point, student, because with due to the small decrease, the separation of these elements becomes possible. Otherwise, it is not possible to separate them. So
Okay.
the M3 ions, we are saying M3 plus ions here, the size decreasing. Instead of this, I may write M3 plus क्योंकि lanthanum I this is La is lanthanum plus. So the size of M3 plus ion is a decreasing, students, and because of this decrease in their size, we will be using them for complex formation, and this will be used for separating separating these M3 plus ions from one another. This is important thing. Ion exchange resin is used for separation, students, because their amount is quite less. Their amount is quite less, therefore they are of great use, and
Okay.
separation is difficult because their sizes are decreasing, but not to that extent. As you can see, there is only a slight decrease. The decrease in size is not very very large, students. The sizes are decreasing. If we have a value of that somewhere, let me see. Okay, not here. Probably somewhere I have given a value of that. Taken some value. Okay. Here, what is the value? Ionic radii in nanometer. Point lanthanum, this is 0.115. This is 0.11 nanometer. It is going up to 0.093 nanometer. ठीक है? There is a very
Okay.
slight decrease. This is not a very big decrease. See,
Yes, sir.
this is a M3 ions nanometer. This table I taken from some source just to tell to you that, because these values help us. When we give numbers, they help us. Now the numbers help us see the values are decreasing, but they are not decreasing to that extent. There is a
Mm.
very slow decrease,
Yes, sir.
and only thing, certain trends are there. We have to know what the trends are, student. What are the trends? Okay. Okay, there is a decrease in the value, students. What values we have shown? Uh, you have seen lanthanum 3 plus, for example, 0.115 nanometer. It is decreasing to Lu 3 plus, which is around 0.093 nanometer. So there is a slow and gradual decrease, and this is what we call as a lanthanide contraction, student. Here we have drawn a picture of that. This is the ionic radii in picometer, and this is the atomic number. So with increase in atomic number, you can see that the ionic radii are decreasing. Ionic radii decreases with increase in atomic number. With increase in atomic number, student, this is decreasing. Now the question is, what is the reason for this? How will you explain this, students? How will you explain? You have an answer, 30 seconds only. Important question for the paper. This has been also called the lanthanide contraction. I said there is another lanthanide contraction which you've seen, which is a consequence of the 4F filled subshell, which you have seen from 3D to 4D, 4D to 5D. You see the sizes were almost same for 5D and 4D series.
Yes, sir.
That was also, we said, due to lanthanide contraction. Now here, what is the result? The 4F constitute inner shell. It is not the outer shell, students. and thus electron is being added. One electron is being added as you move to another element. Every time you move from here to here, one more electron is being added. ठीक है?
Yes,
So
sir.
you are adding one electron each time, one electron added when you move from lanthanum to lutetium. ठीक है?
Okay.
In every next element, the electrons are entering into which subshell? 4f subshell, which is the inner subshell. And due to poor, what we say, ineffective shielding
Shielding of 4f orbitals.
of 4f orbitals, the Z effective, the nuclear charge increases. Nuclear charge is more, so increases, students, and therefore, what will happen? There is a contraction in size, and that is what we say lanthanide contraction. So the result of this is, what is the consequence of this, student? What is the consequence of this? What are the consequences of this? Or I'm talking of what are the consequences of lanthanide contraction? What are the consequences of lanthanide contraction? Can you tell me what are the consequences? You have already seen, because of the completely filled 4F, what happens when we discussed that three transition series, 3D to 4D, what happened? The size increased. But when we discuss the 4D to 5D, the sizes were almost equal.
Almost the same.
So how do we explain that? That was due to the
Lanthanoid
lanthanide
contraction.
contraction. So when we discussed those series, the sizes of 5D contracted because of the poor shielding of the 4F screening effect. 4F. 5D and 4D
Okay.
almost having the same sizes. The increase is not as expected. So that was a consequence of lanthanide contraction, student. Further, more important point to note is that as the ionic radii will decrease, student, the charge density will increase on these metal ions and they will have a greater tendency to form complexes.
Okay.
What I'm saying, what I'm talking, students. Here I said the cumulative effect of contraction of lanthanide, known as lanthanide contraction, causes radii a member of the third series to be very similar to those of the corresponding members. This is the first consequence of lanthanoid contraction. That is why that was also called lanthanoid contraction. Important. This is a very
Okay.
important question for the paper. Very important question for the paper. We know about it. We discussed that the radii of the third series quite similar to 3D, 4D, 5D
3D,
radii.
4D,
5D series radii were quite similar to students
4D.
4D series. So, for example, zirconium, the radius of zirconium is 160 picometer and hafnium is 159 picometer, students. So because of this, they have they account for their two occur in nature together. So because of similar sizes, zirconium and hafnium occur together in nature, are found or occurring in nature together, and therefore it becomes difficult for their separation. because ultimately you want to separate the elements. Then how will you separate? If the sizes are same, then they are together, and it will be a difficult task to separate them. It will be difficult task to separate them because we will be using. But in this case, the second consequence which I want to tell you, the second consequence of lanthanoid contraction, student, lanthanoid contraction is the size is decreased, though small, but they decreased from lanthanum to lutetium.
Lutetium.
The size is decreased, and as the what will happen, ionic radii, when the ionic radii decreases, students, the charge density increases. Charge density means charge by per unit volume. Charge density increases, charge by size ratio increases, and they have more tendency to form complex. So the result of that is complex formation tendency increases, student. This is very important point. Formation tendency increases,
Okay.
and this is the basis of the separation of lanthanides. So this is the basis of, very important question has been asked in other papers also. This is the basis of separation, basis of the separation of lanthanides, ions, lanthanide M3 ions. ठीक है,
Okay.
in in ion exchange separation method, ion exchange column separation technique. That point is very important, student, because this is a very important consequence. The separation is a big challenge for us. These elements are present together, and they are very small difference in sizes, M3 ions. And how will you separate them? That what they do is that if the charge radius, ion radius is less, charge is more, they will form some complex, and complex formation depends on the ability to form complex is more when the charge by radius ratio is more. Charge is more, radius is less. And then in a column, what will happen? The ion, which will be the smallest, M3 plus ion, will have stronger
Okay.
tendency to form complexes. What type of, that we will see, what type of complex agents we will use, some ligands, what type of ligands are used in coordination compounds. Our next topic is complexes and coordination compounds, we will see that. So there you pass it through a column, student, and then that will be the first to come out. The one which is at the bottom will be the first to come out, because in the complex formation, because the size will be the smallest, so we'll have more tendency to form the complex. Therefore,
Okay.
this is the most important property for exam, and will be repeatedly asked in the papers. Will be repeatedly asked in the paper, students. You have noted down.
Yes, sir.
And separation is a question which is very, very important and be asked in many cases. So, what do you expect of the general physical properties, students? Physical properties of the lanthanides, of the lanthanides. One important point is their size difference is not large. Therefore, there will be a, since the size are close to each other, they will have very good similarities in their properties. I'm saying in general, they are having very similar properties. Why? What
Okay.
is the answer? Because their sizes are quite close to each other. Close to each other. Okay?
Okay.
There's not a big difference in the sizes. In the other groups, you have seen the sizes are quite changing. There's a big difference, so the properties could be different. Some covalent, some ionic you have seen, and different. type of compounds are being formed depending on there is a large change in the sizes, students, but here you are not expecting that much change, and they have high melting points, boiling points. They are hard, and they do have electrons, students, to conduct, so they are good conductors
Okay.
of heat and electricity, good conductors of heat, and
And electricity.
many of these La3 plus ions are colored ions, students, and absorption spectra is there, and mostly I'm talking of M3 ions. Plus 3 is the most stable oxidation state, and also they will exhibit magnetic properties. What magnetic properties I've been talking about, students, in the D block elements?
Spin only magnetic moment.
If there are unpaired electrons, there will be magnetic moments. Magnetic moments, what the nature of the magnetic moments can be different, because there we have used only spin magnetic moments.
Okay.
Orbital magnetic moment was quenched, but here the orbital magnetic may not be quenched, then they will have magnetic moments due to the orbital as well as the spin of the electrons. But they will have unpaired electrons. If they have unpaired electrons, then what will they show? Paramagnetism
Paramagnetism.
and other some magnetic properties, like depending on the nature of the electrons which are present, ferry, ferro, or all possibilities are there. So they do exhibit magnetic properties, students. All right, we will continue more about this, which will be oxidation states and other chemical properties in our next class. So this is the first important point here. Their properties,
Okay.
physical as well as the lanthanide contraction, is an important question. Writing electronic configuration and small questions on definitions are always asked to the students. So we have to pay attention to each and every word, and we will be able to meet you in the next class, students, for another session on this.
Okay.
Okay, then.
Okay.
Good,
Thank you, sir.
good night. We will meet you in the next class.
Okay. Thank you, sir.
Okay, students.